Alright, welcome. This is Group 7. We made an infrared MIDI harp. My name is Mitchell.
I'm Chris Moore.
I'm James Gaysek.
And I'm James Demma. So our objective was to create an instrument that could be played hands-free. We decided to go about this by using infrared light. We have an array of infrared LEDs, and they blink infrared light at a certain frequency, and opposite that we have an array of infrared receivers that can receive that light at that frequency. And so you play our instrument by breaking the line of sight between an infrared LED and its receiver. So we have 8 LEDs opposite 8 receivers for 8 notes. So you can play 8 notes at a time just by putting your hands in between the LEDs and the receivers. Our design has 4 major components. We have the input device, which I just described. We have an input board, which houses a microcontroller and a little bit of other hardware that connects our input device to our main processing device, which is our cowl board, which is our third main device. And then our cowl board does all the processing, and then it's connected to our output board, which houses another microcontroller and also has a connection to our MIDI decoder and synthesizer, which we send messages to this little chip, and it creates music for us. And so we have that connected to some powered speakers, and so you play some notes with your hands on the input device. It sends some data to our input board. That relays data to our cowl board for processing, and then that sends processed data to our output board, which it relays to the MIDI decoder, which then produces music for our powered speakers. And that, in a nutshell, is a large overview of how our project works.
Alright, so our project has several objectives. We're going to run through each one and give a demonstration of it as we go. Alright, so first we have the input objectives. The first one is the instrument will take input from a user by using one's hands to play notes. Alright, next the instrument will be able to have 1 octave, which is 8 notes. And as you can see, there are 8 on the bar. The user will be able to select an octave of the 8 available notes. So that means that over here on the web server, we can choose an octave, and the octave is displayed over here on the LCD. And now, when he plays the notes, they're on a different octave. So that's up an octave, and then we can also go down an octave. And as you can see on the LCD, it is displaying -1, which means it's 1 octave below middle C. Alright, the next objective is the user will be able to select from a variety of instruments to play. So when the instrument is turned on, a reset is sent to the MIDI board and it's defaulted to acoustic grand piano. But over on the web server, the user can click on this list, which brings up a list of 127 instruments you can choose from. And then you can select any one you want. And then when you update the instrument, you have a different instrument. And you can choose any of these. Here's another one as an example. Alright, now we're going to go through the output requirements. The first one is the instrument will show which note is currently being played. And when you play a note, it shows, do it so that you can see the visible LED of the note you're currently playing. The next requirement is it should play the sound of the current note, and obviously when you block a note, you can hear it over the speakers. It's also going to show what mode the user's in, and that is displayed down here on the LCD. The buttons change the mode. You have real time, and then you have recording and playback. The next requirement is that you'll be able to play up to 8 notes at once. So So you can block all 8 notes, and all the visible LEDs are on, and all the notes are being played. Alright, you will also be able to record a note sequence, so when you push the yellow button, the mode on the LCD is changed to recording, and you can record a note sequence. And then you push the yellow button again and stop, and your mode changes back to real time. And then you can play back a note sequence. When you push the green button, the mode changes to playback. And then you have the notes that were just played. And there is a time differential for the notes that's saved as well, so it's the same play rate that it was before. And then if you hit the green button again, you jump back to real-time mode, and the LCD displays that, and it stops playback. You're also able to record in one instrument and play back in a different. So if we play back the recorded value, and then we can change the instrument. And now we should be able to play back. And then while we're playing back, we can play in a different instrument. You can also change the octave while it's playing back. And it plays back the real-time data in a different octave than the recorded.
Excellent. Okay, my part of the project was to make the input device. We decided to go with the infrared. As you can see, the receivers we have are demodulated, so they look for 38 kilohertz pulse. To get that working, we use a 555 timer on our board over here, and we're pulsing our infrared at the 38 kilohertz. But at the same time we're doing that, we're also pulsing down the line because one IR can also hit multiple receivers. So we paired them off using a counter, and it has three different bits, so you can run through both a demux on the receiver side and a decoder on the transmitting side. So it'll choose each pair and cycle individually, and we're cycling at 1.3 kilohertz going down the line, so it'll go all the way down and come back, and even though it's cycling, all 8 values are available to the pick, so it can be pulled at any time. For cabling, we decided to go with Cat5, so that way it's very easy to take apart, and if we wanted to make the distance farther apart, closer, we wanted to put the input board somewhere else, you could easily change how this is connected just by the length of cabling used. We used the 568 standard straight through cable. For doing error checking to make sure that our cables are plugged in correctly. The power lines are the same for all of the cabling, so if we messed them up we wouldn't get power and ground opposite. And we also have lights on both boards to tell when we're having an issue or which board isn't working correctly. Also, we have our visible LEDs set up. Each one's paired as well with their IRs, and they have their own bus going from our input board. This is the counter PLD. Here's our 555 timer for the clock for the 2 PLDs, and this is the PLD being used as a demux. This is the main board for on the bars. We have our 2 buttons for recording, playback. We have our decoder that's down here in this mess of wires, and that's controlling the IRs. And we also are using resistors to bring the 5-volt voltage that we're using here down to the 3 volts that the PIC is using for input and output for our buttons. And also this board is the connector between our input board and also going to the other bar. This is our receiver bar, and it's got the multiplexer, so it sends the correct signal back from what receiver you're checking.
I designed our input board. It contains all the same components as the original 45J10 Mark II, except for the external clock and oscillator. We are actually using a 45K20, which has its own internal oscillator. We chose this PIC so that we could get a higher clock speed on it. So from the original Mark II board, it contains all the original I2C hardware, all the original power hardware. It also has 2 PLDs and a timer circuit, and it has 2 RJ45 connectors. One of these connectors is a direct map to port B, which is where we get our LED data from, and the other connector carries power, ground, our 3-bit wide selector signal, and our 2 signals for button data.
So I wrote the input polling code for the input pick, and every time the master, the CAL board, sends the input pick I2C message, it sends along the current note data, and the input pick writes out the visible LEDs to the entire bar, and it also reads the input from port D, which is the encoded state of all of the IR receivers on the other side of the input bar, and sends that back to the ARM.
Hi, I was responsible for our CAL board programming. Right next to me here you see our CAL board task diagram. It shows our 7 tasks, which are in the light blue boxes, and also our message queues for those tasks, which are in the beige boxes. We have a main thread, or main task, which instantiates all the rest of the tasks and sets up the connections for the message queues. We have an input task, which polls our input pick for our input data and recognizes changes in the data and then takes actions based on those changes. Our output task constructs our MIDI messages and our LCD write messages. Our recording task maintains the recording state and the transitions in recording states, and also records notes while we're in a recording state, as well as the time in between those notes. The playback task plays through those recorded notes in time and in sequence when we are in a playback state. Our UIP task maintains our web server, which is how we do configuration changes on our device. And our I2C task maintains all of our I2C communication between the master, which is the CAL, and our 2 slaves, our input pick and our output pick. So now what I'm going to do is I'm going to go through all of our message passing between our tasks to give you an idea of how they interact and what happens on input events. The first input event I'm going to talk about is what happens when we turn on or when we reset. We have 5 messages that occur, all originate at the output task. We send a message to our I2C task, which will relate to the output pick, a reset message, a instrument change message to set our default instrument to acoustic grand piano, and then 3 LCD write messages to set our default settings on our LCD for real-time mode, for our default instrument, and for our default octave, which is middle C. Our input polling occurs in our input task. We poll the I2C task once every 10 milliseconds. It's very precise. We get that regularity and precision through the task scheduler that is built into the free RTOS operating system that we're using on the CAL board. So once every 10 milliseconds we send a message to our I2C task that contains 2 bytes of data, the first of which is a message type, the second of which is a byte of data that represents the current visible LED data that we want to write to our input device. Our I2C task responds by sending a message back to our input task with another 2 bytes, and this is the current note data from our input device and the current button data from our input device. The input task will then compare the current data of notes and buttons to the last poll's data of notes and buttons, and it will act on any changes that it finds. So if there's a change in note input, 3 things happen. Our input task sends a message to our output task to play the note. So then our output task constructs a MIDI data message, which it then passes on to our output pick. And the output task also sends back a message to our input task with new LED data, so that our input task on the next poll can send that LED data to our input device and show with an LED the note that's being played. And the reason why we go through from input to I2C, back to input to output, back to input to I2C again for the note data instead of just lighting on the device whatever is hit on the device is because we have two channels of playback. We have real-time playback and we have recorded playback. So we want the device to show not just the notes that are being played with the visible LEDs, but also the recorded notes that are being played as well.
Okay, I worked on the code for the output pick, and basically it's set up as the I2C slave receiving messages from the I2C master, which is the cow board. There are 7 different message types that it can receive concerning the MIDI board, and those are start on-off messages or start-stop messages for MIDI notes for both channels. The one channel is for real-time MIDI, and the other channel is for recorded playback. I can receive a program change on both channels, and finally a reset message to reset the MIDI board. Okay, so here's the output pick, and housed on top of it is the VS1053B MIDI decoder by SparkFun, and you can see the interconnections between the pick and the breakout board. Most of them are power and ground to set up the MIDI decoder for real-time mode. Here is the reset, which is connected to a GPIO pin on port D on the output pick so that we can send it reset messages. Down here is the RX pin for UART communication between or from the pick to the breakout board. The baud rate is set up for 31,250 BPS, which is standard MIDI baud rate. Here's the ground pin, and then there's a GPIO pin here which needs to be set, and the rest of these pins are for audio connections to the aux jack, which is here, which is connected to powered speakers for audio playback, and VCC, which powers the board.
Alright, I did part of the code for the output pick. The ARM controls the I2C, and the output pick gets 3 types of messages for the LCD, and it shows the current instrument, the current mode, and the current octave. There's the central octave, which is the equivalent to middle C on a piano, and then there are 3 octaves in either direction, 3 lower and 3 higher, and all of those settings can be changed somewhere else in the project by the user. There are 127 instruments. There are 3 modes: real-time, recording, and playback. And the LCD is being driven with 8 pins. It's got a parallel input, and that is all driven with the messages sent from the ARM board. Alright, the LCD shows the current instrument that's been selected, the current mode, and the current octave. There are 127 instruments that can be selected. There are 3 modes: real-time, playback, and recording, and there are 7 octaves. There's the middle C octave on the piano, and then there are 3 in each direction, 3 lower and 3 higher.
What is that supposed to be?
Dun, 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 dun. The end of the Muppet Show.
Ah.
It's the Muppet Show.